How does a countercurrent exchange system work? Well, when you're thinking about a countercurrent exchange system, you need to start by thinking about a source and a sink and draw them on opposite sides of a page like this. And they can be usually in two tubes, but it can also be blood going in one direction and, say, water over the gills in another. So let's talk about a source and a sink, in this case both liquids, and let's look at exchange of something like oxygen, where the source might have 100% saturation with oxygen, and the sink might be 0%. Okay, and remember the direction of movement in countercurrent exchange. We've got opposite direction of movement. So let's set up what would happen as materials are moving through here if the oxygen can cross these membranes. So let's think about the fact that as the blood or water or whatever with oxygen is moving in this direction, that it would be picking up oxygen from the source. So I'm just going to tell you that at this point, let's assume that we're at 98% oxygen here. Less than in the source, but still pretty high. So first question for you is, would oxygen be moving from the source to the sink? And of course, if it can cross membranes easily, the answer would be yes. It's moving down its partial pressure gradient from the source to the sink. A little further along in the source, we'd have lost some oxygen. So let's say we're now at 80%. Down below in the sink, the fluid or blood coming in from the other direction would have gained oxygen, but not as much as at the end, so it's going to be lower. And again, we can look at it and predict accurately that oxygen is going to move from where it's 80% saturated to 78% saturated, down its partial pressure gradient. And if we went further along, the source would have lost more, and the sink wouldn't yet have picked up quite as much. And further yet, we might be at 40 and 20 and maybe 2 at the end, and 38%, 20%, and 0%. And at every point all along here, and in fact you could even presume at every point in between, there would always be a little less oxygen in the sink than there is in the source. The result would be along the full length, oxygen would move, and as long as the pair of tubes was long enough, you'd get to nearly all of the oxygen winding up in the sink and almost none left behind in the source when it leaves. So the result would be, at every stage, we have oxygen moving down its partial pressure gradient from the source to the sink, and at the end the source would have almost no oxygen left and the sink would have picked up most of it. Let's contrast that to a cocurrent exchange. So what would happen if we did exactly the same thing, but we drew it this time as cocurrent? So I'll do the same tubes, and I'll put the source here again, but now the sink is going in the same direction, so I'll write sink down here at the bottom. And let's say we had 100%, and of course the sink is coming from where there's none, so it's 0%. And of course oxygen is going to move, and at some point we might be at 80, and maybe we've gotten to 20 in the sink. Again, oxygen is going to move, and 60 and 40, again oxygen moving down its partial pressure gradient to the sink, and at some point 50 and 50, oops, no longer any movement. And if we go further along, 50, 50, 50, 50. The result is the source leaves with 50. The sink leaves with 50. We've only transferred half. We've only transferred half of the oxygen from the source to the sink. So in countercurrent exchange, where we're moving in opposite directions, we can transfer nearly all of the oxygen or water or heat from the source to the sink. With cocurrent, you get only to halfway in between the two. So that's a countercurrent exchange system. You can quit here. I'll do one more example with heat for those of you who are interested in seeing it. So here's the leg of a dog or a wolf with a really ugly toe pad, and I'll stick a claw on it. And we've got arterial blood coming down. So warm arterial blood coming down, and of course it's using oxygen. So we've got capillaries down in the toes, in the bottom of the feet, and venous blood coming back. And the directions, we've got blood coming down and blood leaving. Okay, and in this case, the countercurrent exchange is with heat. So we might have, up at the top here, we might have blood that's at 37 degrees, and if it's near blood vessels of blood coming to the heart, the blood coming back, the colder venous blood, is colder because it's been down at the feet. It's lost some heat to the environment. And so, but it's been warmed up by being near the arterial blood. So maybe that's at 35 degrees, and we'll get heat transfer from the warmer to the colder. Move down, and somewhere here we may be at 25 degrees, but colder still in the venous blood, and again we get heat transfer. Further yet, maybe down here we're at 15 degrees, and again heat transfer. By the time we're down near the foot, we might be at 6 degrees and 4 degrees, and down here at maybe 4 degrees and 3 degrees, and down at the foot we might be just barely above freezing if our dog is standing on ice. So the result is that along this whole pathway, no matter where we are, we've got heat transfer. So this is countercurrent exchange in a dog or a wolf. Wolves and dogs have very effective countercurrent exchange, and they can have their feet at somewhere just above freezing, so warm enough that it's not causing damage, but they're not losing a lot of heat through their feet too, and most of the heat that's coming out from the core of their body is actually being transferred from the arterial blood to the venous blood. So most of the heat is being recovered. You have the same kind of countercurrent heat exchangers in your arms, but it's much less efficient, and so you can't tolerate anywhere near the cold differences and recover the heat that temperate zone animals like dogs can. Humans are originally tropical, and we function with pretty poor countercurrent heat exchangers like other tropical mammals do.